Welcome to this video that will go through a concept in calculus referred to as higher order derivatives. Higher order derivatives is really nothing more than an extension of what we already know how to do with differentiation. And it's simply where we find what are called like the second derivative, the third derivative, etc., etc. And these are found by basically taking derivatives of derivatives. Just to show you the notation first, if I have f of x, well, we know from our prior work in derivatives, this symbol, f prime, refers to the first derivative. Well, I could put 2 primes there. That means the second derivative. This would imply that for me to take the derivative of the derivative. So on and so forth. 1, 2, 3. If you get up with, you don't want too many of these little prime symbols, you can, I've seen them also sometimes put just a little number up here. So that would mean the fourth derivative. There's also what is referred to as Leibniz notation, L-E-I-B-N-I-Z, Leibniz notation, which looks traditionally like dy over dx. Higher order derivatives with these ones are using a number system, so you put a 2 up here, d2y over dx2. That would mean the second derivative. d4y over dx4. That would mean the fourth derivative. So there's where you put your numbers, above the d in the numerator and above the x in the denominator. We'll use that a little bit here in one of the examples I'll show you in a moment. Okay, so this is a quick, easy section. This one says determine the higher order derivative. So what that wants me to do is continue finding derivatives until I can't do it anymore, which I can do in this question because it's a polynomial, and you'll see why in a moment. So if I find the first derivative, it would be 4x to the exponent 3, take away 6x squared, plus 3. Derivative of a constant is 0. That's the first derivative. This would be what we call the second derivative. 12x squared, subtract 12x. This would be the third derivative. 24x, subtract 12. The fourth derivative would be 24, and then this would be the last one I'd be able to do. So f, I'm just going to do this time. So remember I said you can just put a 5 there instead of 5. That means the fifth derivative would turn out to be 0, and every derivative hereafter would always be 0. So that will be the case when you start out with a polynomial. Series of terms added and subtracted, all to positive exponents. You could eventually keep taking the derivative and eventually hit 0. The key here, though, is you understand that when you take the derivative of the derivative, it's referred to as the second derivative. Now, this one, if I look at it, is asking for, it's hard to make out perhaps on your video, but this is f triple prime, so it's the third derivative. If I was to leave this as it sits, I'm going to get myself into a quotient rule, which is not the best rule to try and navigate through when you have to go through higher order derivatives. So one of the things I would suggest here is that to avoid the quotient rule, we instead do this using this simple notation. So I'm going to take my original function and rewrite it as, just because this is just a constant, put my bracket. The denominator, I'm going to move it to the numerator, and it will switch to 2 subtract 3x. My exponent will become negative 1/2. Square root means 1/2, so if it's in the denominator, you move it to the numerator, it becomes negative 1/2. And now my derivatives should be much easier to do. So let's start with we would need the third derivative. So I have a constant, which just means this number times the constant. You do not need a product rule when it's a constant in front of here. If it was 5x, yes, I would need a product rule. It is not, so negative 5 over 2. 2 subtract 3x, take one off your exponent, and now you need to take the derivative inside the bracket. And there you have the first derivative. Continuing with higher order derivatives, let's take the second derivative. This exponent multiplied by this coefficient will be positive 15 over 4. 2 subtract 3x, take 1 off of this. That'll go down now to negative 5/2. Now, I already have this -3 here. The derivative in the brackets is, again, -3, so I'm just going to switch this to a 9 now. So I multiplied my derivative in the brackets by the -3 that was already sitting out there. There's second derivative. Third derivative. -5/2 times 15/4 is -75/8. 2, subtract 3x to the -7/2. Derivative in the brackets is -3. There's already a 9 out there waiting. That will go down to -27. There you have it. So that's much easier than getting yourself into the mess of a quotient rule. If I'm doing higher order derivatives, if at all possible, I would stay away from quotient rules. Now, sometimes you say, well, what about products? So you have no choice. If it's a quotient rule, you could turn it into a product rule, but you have to do one or the other. So sometimes you just can't avoid it. But if you can, like we could here, it will make things much, much easier doing your higher order derivatives if you stay away from the quotient rule. I'm just going to quickly now show you how this all plays out if it's implicit. So we've looked at implicit in our last section. Let's take the derivative of this expression. So it's a product rule for x, y. So derivative of the first is just 1 multiplied by the second, plus the first multiplied by the derivative of the second, plus 2y dy over dx, and the derivative of a constant is 0. So if I rearrange this to get dy dx isolated, it will be x plus 2y, and this will go to the other side, so -y, -y over x plus 2y. Now, that's the first derivative. We need to get the second derivative. We're going to take the derivative of this. So if you have dy dx, the derivative of dy dx is d2y over dx2. That's how you do it in Leibniz notation. This is a quotient rule. I don't really have much option here. I mean, I could jump this up and make it a product, but I don't know if that would make things much better. I think I'll just leave it like this and take the derivative. So, quotient rule. Derivative of the numerator multiplied by the denominator. Subtract the numerator multiplied by the derivative of the denominator. 1 plus 2 dy over dx. All of this will then get divided by the denominator squared. Okay, this is where it's a little different. We can't leave these dy dx's in my derivative can have x's and y's in it. That's not an issue, but you can't have these little, they're called differentials. You can't have those left in your derivative. So you need to figure out a way, how would I get rid of dy over dx? Well, if there was only something we could substitute in here that we knew was equal to dy dx. If only we could find something, eh? Well, look right above it. Notice what it says. Dy dx is equal to this. So everywhere we see dy dx, we're going to replace it with this expression. So this will now take on this appearance. d2y over dx2. So it's going to be negative dy dx onto x plus 2y minus, let's make that a plus y, 1 plus 2 negative y. So hopefully you see what I'm doing. Anything I highlighted, I replace it with what dy dx was equal to. And this would be all over x plus 2y squared. Now there would be lots of simplifying you could do. I'm not going to get into that, but certainly this would cross this out. Probably over here when you distribute, you could turn this and simplify it up a little bit. But I just want you to get the gist of how you substitute for the dy dx. Truth be told, higher order differentiation is not very common. when you're doing it implicitly, like this one. It's much more common for explicit functions. So here's just one last example where we do some trig. Oops. So I want the fourth derivative. Well, let's start with the first. The first derivative of cosine u is negative sine of u multiplied by du. Second derivative. The derivative of sine of u is cosine, but this negative will just stay there. So it's negative cosine of u multiplied by du. Well, there's already a 5 here. Du is going to be another 5. That'll switch to 25. Third derivative. The derivative of cosine is negative sine. There's already a negative out here, so that's going to switch to positive sine of the argument, 5x, times the derivative of this, which is 5, and there's already a 5 waiting here, or 25 waiting here, sorry, so that'll become 125. Y to the fourth derivative is cosine 5x, derivative of sine is cosine u, multiply that by du, so this multiplied by 5 will give me 625. There's your fourth derivative. So you can see that with this one, you could continue this forever. You're never going to, this number out here is going to keep changing. It's not going to be a derivative like we did in the beginning that will eventually hit 0 because it's not a polynomial. It's a trig function in this case. And that is it. That's how you do higher order derivatives. Our next section, just to give you a bit of a preview, we'll look at scenarios where the second derivative takes on an actual application. And it has some contextual meaning, so we'll use it for something. We'll also do a section later on involving sketching graphs where the first and second derivative also take on some contextual meanings. Usually nothing beyond the second derivative has any kind of an application for us. So I don't want you to think you're going to be doing fifth and sixth derivatives all the time, because you're not. You are going to be doing first and second derivatives very frequently. But beyond that, usually you don't have to worry too much other than those two derivatives. All right, so thanks for watching, and best of luck with just give you a little bit of practice on these, because again, it's not a real major concept, but it is something we have to make sure we're familiar with. Thanks for watching.